video of this part, 8.4, variable size reduction. So you can see here we consider a special case. When we do divide and conquer, every time we reduce the problem size, that could change. Sometimes bigger, sometimes smaller. So there is a interesting example showing that kind of property. Yeah. So let's look at the problem first. The problem, I think you're familiar with this problem. Greatest common divisor. Find the greatest common divisor. So this problem. Yeah. And probably you know the solution. Yeah. But here we need to do a lot of analysis. Yeah. All right. Given two non-negative integers, m and n, but not both 0. M could be 0, n also could be 0, but they cannot both be 0. The reason is simple. If both 0, their greatest common divisor cannot be defined. That easy. Yeah. All right. Now, find their greatest common divisor, GCD function. We define this GCD function of m and n. Yeah. All right. So now let's look at the solution. First, we look at a middle school procedure. So many of you probably like to use this way. In middle school, it is very popular. Here, let me go through all the steps here. First, find the prime factorization of m. Okay, so you know what we will do, find the prime factorization of n. Step 2, find the prime factorization of n. Okay. All right, now find all the common prime factors. After you do 2 factorizations, now you compare for each prime factor, you compare, try to find the common part. The largest common part, actually. Yeah. Largest common part, right? Yeah. Step 4, you compute the product of all the common prime factors. Yeah, you know. Yeah, as much, you know, yeah. So here are some details probably missing. Yeah. So in my description, some details probably missing a little bit. Yeah. Later I use simple example to show. Yeah. And but this method, it looks pretty simple, right? Yeah. But here we want to use a different method. We want to use a recursive method. This one is not recursive, right? So this method is not recursive. Yeah. But to most people, it looks fine. Yeah. Why we need to change to recursive method? Yeah. There is a big reason behind it. A big reason behind it. So what's the big reason? Yeah. We need to change recursive method. Yeah. You will see. Yeah. At some point, I will show you the big reason. Yeah. Let's do this example first. GCD of 60 and 24. Factorization, prime factor, yeah, 2 squared times 3 times 5, the first one. Second, 2 cubed times 3. Yeah. Common prime factors, the largest possible common factors. Factor 2, 2 squared. Factor 3, 3. Factor 5, no common. Factor of power of 5 with exponent greater than 0. Yeah, you may argue exponent equals 0, right? Yeah. So we don't count that part. Yeah. All right. Multiplication, product, you get 12. See? You can easily find the GCD 12. Yeah. All right. It looks simple. The reason is these two numbers very small. Can you imagine if these two numbers are very large, what would happen? Extremely large, what would happen? Can you imagine that? Yeah, so you will get an idea. Yeah. All right. Yeah. So after this example, so now we want to look at the solution here. Yeah. 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 Before we go to the detail of the solution, let me point out, so this method relies on prime factorization. Okay. And the prime factorization for large integers, large positive integer, large m and n, large m and n, it is very difficult. Prime factorization, even you use super power computer, it is still very difficult, very slow. So here I mean, you need to wait long time, hours, even years, if the number is huge. Yeah. I'm talking about several thousand digits. So each number could have several thousand digits. Then extremely hard to do prime factorization. Even years. Even no matter how powerful your computer is, you need several years. So we don't like that method. So for that reason, we want some method without using prime factorization. The reason is the prime factorization is very expensive. Very, very expensive. So we want to avoid it. Yeah. All right, so now you will understand the importance of this recursive algorithm. All right. All right, so we consider special case when n equals 0, it is m, but m cannot be 0. Okay, yeah. All right. The problem size, the maximum of m and n, we know that cannot be 0 based on the given condition. All right. So what is the problem size? So this is the problem size. Okay, yeah. All right. The next question, how do we reduce the problem size? Now, this is the critical part. How do we reduce the problem size? So this is the critical step. If you know how to reduce the problem size, you get a recurrence relation, you get a solution. Yeah. All right. So here you can see this question, that actually is a common way of thinking. Common way of thinking. Yeah. Reduce problem size. Yeah. All right. Next. Yeah. This time our goal, reduce the problem size. All right. Yeah. But in order to do that, we need a special mathematical tool. This mathematical tool is critical here. Without this tool, we cannot reduce the problem size. Yeah. But this tool, every one of you is familiar with it. Yeah. But I just pointed out, you know it, yeah. But it is critical here. Yeah. It's called division algorithm. Integer division. You know integer division, right? Division algorithm. So we write that integer division as a theorem, as an algorithm. So division algorithm. What's that? Division algorithm. Given positive integers a and b, b not 0. b is used as the divisor, so it cannot be 0. Okay? All right? Yeah. There exists unique integers q and r. Unique. That's pretty important. Unique. Yeah. You can only find one pair of integers q and r. Only one pair. Yeah. with the R between 0 inclusive and less than B, greater or equal to the 0, but less than B, strictly less than B. Remainder, R is used as the remainder. You do division, Q as the quotient. So you have the quotient, you have the remainder. That's unique, such that A equals B times Q plus R. That's the integer division. Everyone knows it, but here it is so important. All right, so when we use this algorithm, we can assume m greater or equal to n greater than 0. Because for the 0 case, we can get an answer immediately. So we exclude those special cases. All right. So when we apply this division algorithm on GCD problem, we use m in the formula as the A and for B. Then QR could be found, right? Could be found. We don't worry, our program can do it. So we don't worry. We don't need to find it. We make our program do it. All right. So now we have this new expression, the formula. Next, we need to do problem reduction. So how to do problem reduction? We need to develop a key property to get that problem reduction. What kind of key property? Transformation. So you can see in the important stage, we need to do formula transformation. Here, we need to do that another time. Okay. So what kind of transformation? Look at this. GCD. In GCD, the m has this new expression, so we replace m by qn plus r. All right? Okay? We try to simplify this new expression. But when we do simplification, we look at this transformation. Division transformation. M over n, division, the fraction way, division. We can get the quotient, the integer part, q, plus the fraction part, r over n. How about that? So that's the transform we have. Okay? All right. Now, you can you see the q part, integer part is gone. The GCD of m and n is the same as the GCD of r and n. Can you observe that? The integer fraction part, integer part we can remove because the integer part will not change the GCD. Can you see that? The integer quotient part will not change GCD. So with that observation, we can just cross out that NQ part. And we get GCD of n comma r. This time, can you see the problem size reduction? Can you see the problem size reduction? Yes. So you can see that is the problem size reduction. But we can keep reducing the problem size in this way. Another integer division, another round problem size reduction like this. So let me use a simple example to show you how we do the problem size reduction. Example. Same example, but this time we put an n here, 12 remainder. 60 divided by 24, the remainder is 12. So we reduce to another GCD problem with smaller problem size. Then another reduction, this time 12, remainder is 0. If remainder is 0, you can write the answer of the first number immediately. We know it's trivial. So we can write the answer 60. I mean, the reason we can, we can do that reduction because we have this, right? This method, you can see, using the problem size reduction, you can easily see we do not need to do prime factorization, right? This method does not rely on the prime factorization. Then we won't have that bottleneck. It's a huge bottleneck problem. Prime factorization, it's a huge bottleneck. As I said, so if the number is huge, thousands of digits, you need years to do the prime factorization. You cannot imagine how slow it is. So we don't need that. We don't want that. With this method, you don't need that long time, right? You don't need that long time. You can do much, much faster. No prime factorization. So it will be pretty fast. Division, multiplication, those operations pretty fast. All right. So next, we will look at the implementation. After we do the problem size reduction, at the end, we need to do implementation. So this method is called Euclid's algorithm. Very famous. More than 2,000 years old, Euclid's algorithm. This is a very famous algorithm. All right, so the rule, we know that. We write this rule. GCD of x and y, both non-negative integers, but they cannot be both 0 here. When y equals 0, it returns x, but the x cannot be 0. Okay? If you detect both 0, your function return some, flag or, some special tag. All right. So next, when x is a multiple of y, we use this, percent sign, that sign, mod operation, right? Modular operation, mod. X mod y equals 0. That means x is a integer multiple of y. So then the answer is y. Otherwise, GCD of x, x mod y. Remainder, x mod y. That's the remainder part. All right. So with this relation, we can easily write our code, implement this function, recursive function, in this way. All right. All right. Let's write the code here. Pseudocode here. So you know the meaning. All the possible cases. The first one, we check the both x0, y0, it returns -1. -1. So when you see the negative number, you know what's the meaning. Other than that, so each case we can implement, right? So each case we can implement. Then the third one we can implement. So pretty straightforward. So this is the variable size recursion. The size reduction variable. All right, so we complete our first part of recursive algorithms. All right, so we start.